Hello and welcome back to Calculus 1. This is section 5.5 about the U sub. It's a part 2. All right. Just need to finish a few of the concepts we didn't get to last time. We talked about the U substitution being very helpful in a situation when algebra would be either not helpful or really annoying, as x plus 3 to the 39. We are technically swapping the variable x for variable u, changing the domain of the problem, and the resulting integrals would have the same value at the end. So it's a very interesting procedure, and we did a whole bunch of these, as you can see, examples. What's left for us to talk about are definite integrals. Definite integrals have limits, and those limits belong to the domain x. If we are switching domain x to the domain u, we better switch the limits as well. So that's the new part that we have to talk about. So what I have here, when I write a to b of f of x dx as the integral, we need to understand that x1 is a and x2 is b. And those x1 and x2, which are a and b, are on the number line x. So if I am switching the variable from x to u, I have to switch everything, which includes the limits as well. Now, to switch limits, it's very easy. All you need to do is to just compute all the limits in your u sub equation, right, that you picked. So for these problems, we can go and let's just take the very basic example as the first example. So let's say 0 to 3 of e to the 5x dx, right? So this is the first one. Trying to get to the book. There we go. So we know that our substitution u is equal to 5x, du is equal to 5 dx, and I don't have 5, so I can fix that by placing 5 and 1 over 5 in front, as we discussed. And I have 1/5 integral. Now, I used orange, right? 5 dx, that's going to be du. So I have e to the u du. So now, what is new? Here's what's new. New stuff is, to calculate u1, we will take 5 times 0 and still have 0. And to calculate u2, we'll take 5 times 3 and get 15. And the upper limit is 15. So all you need to do is to take the lower limit, plug in a u sub equation, and come up with a new lower limit. Then you take the upper limit, plug it in the u sub equation, and you come up with a new upper limit. So you transform your limits from x to u. Now that's a good deal, because you transformed your limits, and you don't have to go back to x variable to compute, because now you computed the integral in u, and your limits are u, so you just forget to plug them in. So for indefinite integrals, you use u sub, and then you use x, you go back, right, to the x variable plus c. But if you have a definite integral, you switch integral to u, you switch limits to u, and you immediately compute without going back to the variable. So now, what is the integral of e to the u? Well, it's e to the u. So we have 1/5 e to the u computed from 0 to 15, which is 1/5 e to 15 minus e to the 0, which is 1/5 e to 15 minus 1. And this is a number. You can punch this in a calculator and get decimals for it. This is just a standard, right? Exact solution. That's what it is. It's exact solution. So the only new thing that we are introducing today is the part where, in addition to transforming the integral, you also transform the limits for that integral. Let's do another 4 or 5 examples. I hope you also see that it's very beneficial to practice these problems because they do pretty much everything, right? Integration, U sub, and switching the limits. So they're very valuable. So 45 through 74 in the textbook. In the new textbook, the 3rd edition textbook. So let's take a look at some of the problems. Say you have problem 48 as the integral from 0 to 2, 2x divided by, open parenthesis, x squared plus 1, everything square, dx. Go. So what is U?
X squared plus 1.
Good. X squared plus 1. Then du is 2x dx, which is great. We have exactly 2x dx. That's great. Did we all get 1 and 5 for limits? We good? 4/5? I know how much you love trig. Integral 0 to pi over 4 sine theta over cosine cube theta d theta. I gotta restock. I ran out. All right, let's take a look at this problem together. Now that the happiness is on the horizon. What is u?
Cosine theta.
Very good. See, cosine is cubed, which would prompt us to have u cubed, and that's good. And we also need derivative always. You can write this as a sentence. We need the derivative always to be multiplied to d theta, so that you can, because d theta has to be in, right, du has to stay in the numerator. So the derivative of this is du is negative cosine, negative sine theta d theta. I don't have this negative, so I'm going to fix that by placing -1 in front. And so this becomes negative integral. And now I have negative sine theta d theta. That is just my du. And the bottom is u squared. Now the limits. u1, which is the lower limit, is going to be cosine of 0. And that is 1. And the upper limit u2 is cosine of pi over 4, which is very good.
How did you get? Where does the cosine come from in U1?
Whatever the formula is.
Oh, okay.
Right? Whatever the formula is what computes the limit.
Okay.
So, now, what's bigger? 1 or root 2 over 2?
One.
So we should put that on top, right? And that's how minus goes away. So now I have -1 over 1 minus -1 over root 2 over 2, which is -1 plus 2 over root 2. You flip because of double fraction, and you can rationalize now root 2. So this is 2 root 2 minus 1 over, no, I lied, minus 2. Okay. Does it make sense? Maria, go. All right, see. Have fun. You can see the happiness, the joy. So when I rationalize, root 2 times root 2 is root 4. Root 4 is 2. And then I find common denominator with the first one, which is 2 over 2. So, and then I put the negative second. Oh, and then I cancel the 2's. Right? Should have done that a long time ago. So this is just root 2 minus 1. There we go. That's much better. Because 2 cancels these two. And it's just root 2 minus 1. Great. Yay. Posted this one on my Instagram story yesterday. No, yesterday, 2 days ago. Wrote checkmate in 2 steps. It looks terrible. Let's see what you got.
That's how I like
Mm-hmm. So what's you?
Cosine.
Is there a sign somewhere? Ooh,
No.
no. What's you? Yes. There is no sign. So we cannot pick cosine. It has to be function derivative pair. And we don't have it with a cosine. Now e to the w has an e to the w in front. So that's a function derivative pair. So we're cool there. What's my du? It's e to the w dw. I have that. E to the w dw to satisfy the du needs. We also have to calculate u1. That's going to be e to the ln pi over 4, which is just pi over 4 because e and ln will cancel. u2 is e to the ln pi over 2, which is pi over 2. So the integral now becomes pi over 4, pi over 2 of cosine u du. Very simple, right? The next step is the solution for this, so that's why I said checkmate into 2 steps, right? what is cosine of, I mean, integral of cosine u? Very good. From pi over 4, pi over 2. So we have sine of pi over 2 minus sine of pi over 4, which is 1 minus root 2 over 2. Done. Let's do one more. Ooh, I almost forgot about this one. Depending on how much you practice, these things become very obvious quickly, actually. But then you run up into a problem like this, and then you start losing hair. This one requires advanced knowledge of integration. See, we don't have x on top. So we can't put 9x squared plus 1 as u. Because that will have 18x. 18x as a du. And we don't have x. X you can't fix. You can fix constants, but you can't fix if you're missing a part of a function or a function. So this one is very tricky. Does anyone see what this could be? Does anyone see it?
Do you have to put a negative exponent by the on the bottom? And put it on the top.
What is it? It's hard. How about if we don't worry about does this form remind you of something that you have seen before? It was your second exam, actually.
Like logarithmic in some way?
No. Something that had this as the answer. Around. It wasn't on your second test, but it could have been, and I said, if it's there, formula is not going to be given. You have to know it.
Is it an inverse trigonometric function?
Inverse trig, yeah. Which one? The one that you absolutely must know.
Tangent?
Yes. This is inverse tangent. So the prerequisite knowledge here, written in blood, is that the derivative of the inverse tangent is 1 over 1 plus x squared. This is the formula that is there. Which means that the integral of 1 over 1 plus x squared dx is inverse tangent x plus c. So this is the knowledge that I'm going to put in a box, which you are supposed to have, because I said out of all 6 inverse trigonometric functions for derivatives and integrals, you better know this one, right? Now the issue is that you don't exactly have x squared plus 1, you have 9 x squared plus 1. So the way to fix that is to make this thing something squared, u squared, right? So how do you make this u squared? Well, we go and we say 3 squared times x squared can be written as 3x everything squared. And this is where u kicks in. U equals 3x, du equals 3dx. I don't have the 3, so I will multiply by 3 and divide by 3 on the outside. So now the 4 will have to kick 4 out. Kick the 4 out. So we have 4/3 integral. And now in orange, 3dx is my du. So I have 1 over 1 plus u squared, or u squared plus 1, doesn't matter, du. And that is exactly the form for our inverse tangent. My u1 is going to be 3 times 1/3, which is 1, so that's the bottom limit. And then u2 is 3 times 1 over root 3, which is 3 over root 3, and then we rationalize, so the whole thing is just root 3 on top, because root 3 times root 3 is root 9, which is 3, and they cancel. So now I have 4/3 inverse tangent of u computed from 1 to root 3. That's 4/3 inverse tangent of root 3 minus inverse tangent of 1 which is 4/3. Inverse tangent of root 3 is pi over 3, and inverse tangent of 1 is pi over 4. So this gives me, when I subtract, pi over 12, and these cancel for a total of pi over 9. Does any of this make sense? Kinda, sorta. So integration is a procedure, right? We need to know derivatives. And the tricky part here is to see the form of inverse tangent and know it. As soon as you know that you are supposed to have a single thing squared plus 1, which is the reason why I wrote that 9 is 3 squared, so I can pull that square, which leaves me with what u is inside the parentheses. There is one more problem somewhere like this. Well, yeah, it's somewhere in here. Maybe on the other side. Yes, here it is. Problem 68. It's much worse because you have 25. Stuff like this pops up in Calc 2, not here, but still. 0 to 6/5 dx over 25x squared plus 36.
That's 6/5.
6/5, yes. This can be solved by trigonometric substitution as well. But when you look at this problem, you say, oh, well, there's my x squared plus 1. It doesn't look like it, but, you know, it's going there. So, how do we do this? Well, the trick is to first make plus 1. And there's a lot of steps involved. I have to divide top and bottom by 36. So that's 1 over 36 in front of the integral. And inside the integral I still have my, well, I can put 1 over 25 over 36 x squared plus 1. You see, that was my first step, was to make that plus 1, because our formula requires plus 1. Now we do the same trick. This is 5 over 6 squared x squared, which is 5 over 6x everything squared. And that's how I know what the u is. U is 5 over 6x, which means that the du is 5 over 6 dx. I don't have 5 over 6, so we are going to add in 5 over 6 and 6 over 5 on the outside to balance it. So now these guys cancel. You get 1 over 30. The integral 5 over 6 divided by 5 over 6x everything squared plus 1 dx. So now you have your 5 over 6 dx, 5 over 6 dx, so that's du. It's 1 over 30 integral. The limits are still 0 and 6/5. 1 over 30, and now we have du over u squared plus 1, which is tangent. Now we have to transform limits and we're done. So u1 is 5 over 6, putting the bottom limit times 0 is still 0. And u2, which is the upper limit, 5 over 6 times 6 over 5. Look at that. That's 1. Nice. So we went from that crazy, terrible integral into something that it's really manageable. 1 over 30, inverse tangent of u, computed from 0 to 1, which is, inverse tangent of 1 is pi over 4. So, well, let's write it out. So 1 over 30, inverse tangent of 1 minus inverse tangent of 0. Now inverse tangent of 0 goes to 0. And what I'm left with is 1 over 30 times pi over 4, which is pi over 120 as the final answer. And that's the course. We're done. Right? You gotta know this though, right? Bye.